Okay, let's do an example. So basically we are looking for the solution of, let me use phi, is equal to minus 4 pi Dirac delta 4 pi q r minus r prime. This time in cylindrical coordinates. You see, if you remember when we were discussing the addition theorem for spherical harmonics, what we had done was we had the system, we put our charge over here, and then used spherical coordinates to show that this 2 YLM omega YLM omega prime sum over m. We had some certain coefficients over here. This was equal to PL of cosine gamma. So this is how we had derived the addition theorem for spherical harmonics using the uniqueness of the solution of the Poisson's equation. Now let's try to obtain a similar relation in cylindrical coordinates. You see, this YLM is a part of the general solution in spherical coordinates. Now in cylindrical coordinates, we will basically do the same trick. We will assume we will divide our region into two. A cylindrical region that contains the point r is equal to 0, and our charge is on this surface. So inside the cylinder, outside the cylinder, the potential satisfies the Laplace's equation. Only on the boundary it doesn't satisfy the Laplace's equation. Now let's write the most general solution in cylindrical coordinates. Now the Laplacian of phi in cylindrical coordinates is just 1 over, well, let me use the notation S del by del S, S del phi by del S plus 1 over S squared del squared phi by del phi squared plus del squared phi by del z squared. Well, even in the inside region, I will also divide it into two. Or let me just keep it this way for the time being. Now, what do we want? we in separation of variables, r will be a function of s, coordinate phi, and z. We will assume that it is written in the form a function of s only, a function of this phi coordinate only. Well, let me use a different symbol. Of this phi coordinate only, and a function of z only. And then if we just say 1 over the potential times the Laplacian of the potential, which should be equal to 0 in all our regions, this is equal to 1 over the function s, 1 over s d by ds, s times the function s, derivative of the function s, plus 1 over p, 1 over s squared, the second derivative of this function p, plus second derivative of the function z with respect to z. One over z. So this is our equation. This should be equal to 0. Now let's get part by part. This part depends only on z. The other part doesn't depend on z. But this equation should be satisfied for all possible values of z. But that basically means that the part that can depend on z should be independent of z. So this implies that 1 over z, d squared z by dz squared is some constant. Let's just call it C1. I don't know what that constant is yet, but it should be a constant. So what remains? 1 over capital S, 1 over small s, d by ds, s, ds by ds, plus 1 over s squared, 1 over p, the second derivative of p with respect to phi squared, plus C1. This should be equal to 0. Now again, this part is the only part that might depend on phi. All the remaining part depends only on s. But if this equation is satisfied for all possible values of phi, that part should be independent of phi. Or that part should be a constant. 1 over p d squared p by d phi squared should be equal to minus m squared. Well, why did I choose it to be minus m squared? I already know that it should be periodic, and if it is periodic, it should be a sine or a cosine, and then for a sine or a cosine, the second derivative is a negative number times itself. So that's why I choose it to be m, minus m squared. And then we have the last one. Plus 1 over s squared, or minus m squared plus c1. This is equal to 0. Or, let's say, let's multiply both sides by s squared and s. Take that derivative, and we end up having s squared d squared s by ds squared plus s ds by ds minus m squared s plus c1 times s squared s. This is equal to 0. This is the equation that the s part should satisfy. Now let me change the question a bit. You see, the solution of this equation turns out to be Bessel's functions, etc. So I would rather avoid that. I would like to change my problem not to this point charge, but this infinite wire. So it's no longer 1 over r minus r prime in cylindrical coordinates. It's not this equation, but we have this line charge density. I just modified my problem a bit. Well, this basically tells me that, although this is still valid, this general derivation, my phi is independent of z. It should be independent of the z coordinate. But this tells me that C1 is equal to 0. You see, the only possible z dependence was from this function z. It should be independent of z, so its derivative is 0. So C1 is 0. What remains is s squared d squared s by ds squared plus s ds, the function s, divided by ds minus m squared s. This is equal to 0. Now we need to solve this equation. Do you know the solution of this equation? You do. No, you see, just look at this equation. You take the second derivative, multiply by the second power of the argument. You take the first derivative, multiply by the first power of the argument. So the solution of this equation is s to some power. And we need to find two independent powers. Because it's a second order equation, second order linear equation. There should be two independent solutions. Now let's see. If you put it over here, you would end up having n times n minus 1 times s to the n plus n times s to the n minus m squared s to the n is equal to 0. I can just cancel s to the n's. I end up having n squared minus m squared is equal to 0, or n is equal to plus minus m. Now we have these two solutions. S is equal to, let's say, am times s to the power m plus bm divided by s to the power m. Well, these are two solutions if m is not equal to 0. Well, if m is equal to 0, okay, we have the constant solution, but both of them are constant. So, I mean, this solution doesn't give us the two independent solutions. We have to find the two independent solutions. So let's say if m is equal to 0, we... Why? No, am should not be 0. You see, if m is equal to 0, this solution is not a solution. I mean, it's just a constant. It's just am plus bm, a constant, a single solution. And if you look at our differential equation, indeed, s is equal to a constant is a solution of our differential equation if m is equal to 0. But that is one of the solutions. We have to find the other one. Now let's look at our equation if m is equal to 0. In that case, our differential equation is actually this one. I divide it by s. This is our differential equation. But this is equal to d by ds of s ds by ds. And so s times ds by ds should be a constant. Let me call that constant a0. Or the derivative of s with respect to s is a0 over s, which tells me that this function s should be a0 times the logarithm of s over s0 plus b0. In fact, I can even set b0 equal to 0. This is another solution of my differential equation. Or, I mean, if you don't intend to be very formally correct at every aspect, this is equal to a0 logarithm of s minus a0 logarithm of s0, which you can just call as b0, if you like. But of course, this form formally doesn't really make sense because s has a unit and you cannot talk about the logarithm of a unitful quantity. So the more formally correct expression is this one over here. So now we have our solution. The solution depends on s and also on the phi coordinate, but not on the z coordinate. And that is, for m is equal to 0, we have a 0 logarithm of s over s0 plus sum over m, let's say from 1 to infinity, am times s to the power m plus bm 1 over s to the power m times cosine m phi plus delta m. So this is our general solution in cylindrical coordinates of a potential that is independent of z. Now let's go back to our problem. Now, inside the cylinder, you see, inside the cylinder we have the S is equal to 0 points. At S is equal to 0, the potential has to be finite. If the potential is finite inside, that means that A0 has to be 0. And in fact, now let me call that coefficient B0. B0 should be 0, and Bm should be 0 for m larger than 1. Because Bm terms also diverge at S is equal to 0. So phi inside is actually equal to m is equal to 1 to infinity am. Now let me put it in this way. B0 plus m is equal to 1 to infinity am s to the m cosine m phi plus delta m. Well, I said that B0 has to be 0. Well, let me put a tilde if you like. In a sense, right, but I don't know what S0 is. B0 times logarithm of S0 can be finite. Well, that is the nice thing about this form over here. The first A0 logarithm of S term has to be 0, not the other one, to be finite. So this is my potential inside. Now there is the potential outside. Well, the potential outside need not go to 0 at infinity. That's kind of the problematic part. So B0 logarithm of S over S0 plus m is equal to 1 to infinity am s to the m plus bm 1 over s to the power m times cosine m phi plus delta m. So these are our potentials inside and outside. Now I need to find these coefficients. Well, let's say, what is my chart? What I know is the electric field outside a given surface minus the electric field inside a given surface, inside the same surface. This should be equal to sigma over 4 pi sigma in the normal direction. Well, we know that if we have a charge distribution, the tangential component of the electric field over that surface charge density should be continuous, but the normal component need not be continuous. There will be a discontinuity, and that discontinuity will be given by the surface charge density. Now here I have a surface charge density. Now the surface charge density will be a function of phi and z. And, well, a line charge density I can write as a surface charge density and also as a volume charge density. Now here the discontinuity in the electric field is proportional to the surface charge density. So this line charge density, I have to write it as a surface charge density. And the surface charge density is nothing but delta lambda Dirac delta of phi minus phi 0. This is my phi 0. So I have a surface charge density. Now I know that the potential has to be continuous on the surface. Well, let me put a delta over here also. The deltas can be different. So the continuity tells me that B0 tilde plus m is equal to 1 to infinity am, let's say the radius is r to the power m cosine m phi plus delta m. This should be equal to B0 logarithm of r over S0 plus m is equal to 1 to infinity am r to the power m plus bm 1 over r to the m times cosine m phi plus delta m tilde. This should be satisfied for all phi. Well, this basically tells me that b0 tilde is equal to b0 logarithm of r over s0, a m r to the power m. Let me put these tildes. They can be different. They don't have to be the same as the previous ones. And a m r to the power m, this is equal to a m tilde r to the power m plus b m tilde 1 over r to the power m, and delta m is equal to delta m tilde. Otherwise, the equality will not hold for all values of phi. So this is one relation between our two sets of parameters. Now we need to find one more relation between these two sets, the A parameters and the B parameters. And that set we can just obtain using this relation. Well, the normal component is now the S component, perpendicular to the surface, d phi by ds, as S goes to R from the positive side, minus derivative of phi with respect to S as S goes to R from the negative side. This should be equal to 4 pi lambda Dirac delta phi minus phi 0. Well, I know my phi's. So minus del phi by del S, when S goes to R from the minus side, well, it's basically the derivative of this term over here with respect to S. Evaluated at S is equal to R. And if you take the derivative, this is minus sum over m from 1 to infinity, a m s to the power m minus 1 m cosine m phi minus delta m. On the other side, derivative of phi with respect to S, evaluated at S is equal to R plus outside my cylindrical volume. This is my potential. Which will be equal to minus del over minus B0 over S and minus M from 1 to infinity a M tilde M S to the power M minus 1. Well, here of course S is now R. Here also S will be equal to R. Minus M Bm tilde over R to the power M plus 1 times cosine M phi plus delta M tilde delta M. Now I know both of the derivatives. So if I take the difference, this is equal to minus B0 over S. Let's see, minus m from 1 to infinity. Well, all the derivatives are proportional to m, a m tilde r to the power m minus 1 minus b m tilde over r to the power m plus 1 plus a m r to the power m minus 1 cosine m phi plus delta m. This should be equal to 4 pi lambda Dirac delta phi minus phi 0. Well, to start with, you see the right-hand side is a function of phi minus phi 0, not of phi only. The left-hand side should also be a function of phi minus phi 0, not phi only. So it basically tells me that delta m is nothing but minus m phi 0. Now the second thing we will use is, let's say, just multiply. We have on the left-hand side, we have these terms, m phi minus phi 0. Multiply it with, let's say, cosine n times phi minus phi 0. Integrate it from 0 to pi, 0 to 2 pi. In fact, 0 to pi should be enough, or 0 to pi should be enough. So what is this value? Yes, pi over 2 Kronecker delta mn. On the other side, this is equal to from 0 to pi d phi cosine n phi minus phi 0 times Dirac delta phi minus phi 0. This is equal to cosine 0, which is 1. And hence, just we have this relation over here. Take that relation, multiply it with cosine n phi minus phi 0, carry out this integration. You will end up having, is this true? Is from 0 to pi or 0 to 2 pi?
These are even functions. These are even functions.
That should be enough, 0 to pi. So what that gives us is, well, let's say minus b0. Okay, this is not s, this is r. So let's look at the m is equal to 0 term, minus b0 over r. Let's just integrate, or without multiplying by anything, integrate from phi from 0 to pi. Phi 0 is between that interval. So we would have 4 pi lambda. B0 is equal to minus r 4 pi r lambda. So we already know B0. Really? Well, that is cosine 0. Cosine 0 is 1. Why? Well, you see, we are just using the property of the Dirac delta. The Dirac delta tells me that wherever you see a phi, just substitute phi 0. So when inside I have the cosine n times phi minus phi 0. In place of phi, put phi 0, that is cosine 0. So you see the Dirac delta has this property. Dx, Dirac delta of x minus x0, f of x. This is equal to f of x0. If x0 is in the range. So I'm not really subtracting the values of a function at the two boundaries. It's just the Dirac delta. And then what else? We have this combination. Multiply by pi over 2. This should be equal to this is also 4 pi lambda. With a minus sign. And what we had already found one relation. So these we already had it from the continuity of the potential. These two relations we obtained from the discontinuity of the electric field at the surface. And so we can just basically determine what these A and B coefficients are. Not exactly though. Let's see. We already know what B0 is. And from B0 we can either write B0 tilde or S0 from this relation. Well, the problem is since you can always shift the potential. So S0 is not really uniquely defined. So that's not a problem. You can choose S0 whatever you like, as you wish. I mean, it's basically setting the potential to 0 at some point. We didn't set the potential to 0 at infinity. So that is kind of one problem we are having here. And furthermore, okay, so we know B0 and B0 tilde. Then we need to determine AM tilde, BM tilde, and AM. So we have 3 sets of equations, but only 2 equations. Now 3 sets of unknowns, but we only have 2 equations. So that's kind of one problematic region we have over here. The problem is that, okay, we are looking at the junction between these two surfaces, but I mean, the volume we have has a boundary at infinity, and we didn't specify what the potential at infinity should be. So we have to choose it somehow. What should be our potential at infinity look like? So we are not really specifying all our boundary conditions. So that is where we have this ambiguity. Okay, we know that the solution is unique given the boundary conditions, but in this problem we didn't specify all the boundary conditions. We only specified the boundary condition at origin, at the z-axis, at the interface separating these two domains, but we also have a boundary at infinity. And since we didn't set it to 0, we didn't actually do anything for the potential at infinity. We didn't say anything. So that is why we cannot obtain a unique solution yet. So that is where the ambiguity comes from. So we have these 3 sets of unknowns, only 2 equations, so we can express these 2 sets in terms of the 3rd set. And the 3rd set we can only determine by the boundary conditions at infinity. Well, this is kind of a pathological example because we have the charges itself, they go to infinity. So we don't really know what the charges are. But we can kind of cheat a bit. We have this infinite wire. At infinity, it will be almost as if it is at the origin. At infinity, the potential well, the infinite potential is the logarithm. It should be logarithm of s. It should be proportional to logarithm of s at infinity. Let's say s over s0. S0 is kind of arbitrary. The proportionality constant should be, what should be the proportionality constant? 2 lambda, 2 pi lambda. The potential is 1 over s. The electric field is 1 over s with a factor 2, right? Okay, let's solve it. We have an infinite wire. We take such a Gauss surface, charge density lambda. If you integrate the E dot ds, this is 2 pi sh times E. And the Gauss law tells me that this should be 4 pi h lambda. So E is equal to 2 over s, 2 lambda over s. And if you integrate this, you get the logarithm of s over s0. Again, s0 is kind of arbitrary. But this basically tells me that if you look at our potential outside, this is the outside potential. So when s goes to infinity, I should only end up having this b zeros. I should only have that b0. b0 term. Now this b terms, they anyway go to 0. A terms, they diverge, but they shouldn't be there. So a is 0. So this condition tells me that am tilde is equal to 0. Furthermore, b0 is equal to, or was it b0? b0 should be equal to 2 lambda. Well, I probably made a mistake somewhere else in the derivation. You see, we are in the outside region. We know what it looks like at infinity. Or maybe I should probably say that this is S0 tilde. So in that case, B0 is 2 lambda logarithm of S0 over S0 tilde or something like this. Then, of course, we still need to determine that S0. That will fix the ambiguity, probably. So now this is AM tildes are 0, BM tilde and AM, they are related by this relation. This is one of the relations. And they are also related by this relation. This is the second relation. And you can solve for both of them. So if you go back to your question, can we have this logarithm? Well, yes, we do. Actually, if you have an infinite wire, the potential is a logarithm only. An infinite wire at origin, along the z-axis, the potential is a logarithm of the distance from the wire. So we do have that logarithm. Yes, any last minute question?
can we do a distribution collection of wires?
Oh, so you have a shell? Yeah, sure. You can write it as a collection of wires. If you know the charge density, then you are done. What is the potential inside? Or let me give this plus. Both of them are plus. Well, the potential, you know the boundary values. That's enough. No charges inside. Well, you see, what you should do, well, this separation of variable ansatz is still the same. Now we have this z dependence, so you cannot say that C1 is equal to 0, but keep in mind that z is periodic. You start from plus V0 and go to plus V0. It should repeat itself along the z-axis. So that tells you that C1 has to be negative. C1 is negative. Well, the phi part, there is no change over there. In fact, the problem doesn't depend on phi because it has this rotational symmetry. So that you should be looking for a solution that is independent of phi. And then this is your equation with m is equal to 0. C1 a negative constant. You have to look up what the solutions of this differential equation are. And then just look up some of its properties. What does it look like? And you are looking for a solution that is finite on the z-axis when s is equal to 0, and a solution that can go to 0. So this will be, you will have two solutions of that differential equation. One of the solutions, if I'm not wrong, it probably goes to 0 along the z-axis. And then you should find the other one. One diverges along the z-axis, s is equal to 0, the other one is finite. And then you just write down the general solution. In this problem, you don't have inside and outside, you only have inside. And then once you write the general solution of the potential, you have to match it with the boundary conditions. When s is equal to r, your solution should be 0. That is one boundary condition you have. And, well, depending on how you position your origin, I might suggest you to put the origin at the center of the cylinder so that when z is equal to minus h over 2, your solution should be plus v0, and when z is equal to plus h over 2, your solution should be v0. And that will tell you what the unknown coefficients, constants are. And let me give you one more homework question. Homework question 1, homework question 2. You have this cube. Okay, position it properly. Of side length L, X, Y, and Z. There is a point charge Q inside. So, and the cube is grounded. So basically you are looking at the Green's function. What is the Green's function inside the cube? Again, I will give you a hint. So let's say that this point Q is at the point x0, y0, and z0. Your potential satisfies the Laplace equation, for example, when z is less than z0 and when z is larger than z0. So you have these two domains, z less than z0 and z larger than z0, and you satisfy the Laplace equation. Now, then in each one of these domains, you can make this ansatz in each one. And now, in each one of these domains, x and y should be periodic because it repeats itself. It has zero value at some point and zero value at the other point. So that tells you that d squared x by dx squared should be equal to minus m squared x. D squared y by dz squared should be equal to minus n squared y. And d squared z by dz squared should be equal to m squared plus n squared z. Of course, you have to show that these should be the equations in your homework. So the general solution for z less than 0 and z larger than 0 would be sine n pi over L x sine n pi over L y and e to the power m squared plus n squared z minus e to the power minus m squared plus n squared z and this is true for z less than 0 because at z is equal to 0 it should also go to 0. Here we have pi squared over L, pi over L with certain coefficients a and m. And then for phi z larger than 0, the solution is b and m sine n pi over L x sine m pi over L y e to the power pi over L m squared plus n squared, well this is square root z minus L minus e to the power minus pi over L m squared plus n squared times z minus L. Again, it should go to 0 when z is equal to L, not 0, z0. Below the charge and above the charge you have these two solutions satisfying the boundary conditions. Then you have to match it at the interface. If you approach z is equal to z0 plane from above or from below it, you should have the same value plus e outside minus e inside. Well, you can just choose your normal direction to be the z direction. So outside is z above z0, inside is z below z0. This should be equal to sigma, which is q Dirac delta x minus x0, Dirac delta y minus y0, 4 pi sigma in the z direction. And this will allow you to determine, these two equations will allow you to determine these a and b coefficients. So you only have 2 questions for next week. I mean, you will spend enough time on these. Any questions on the homework, on other stuff? So see you on Friday.